Right now, beams of light are racing toward you at an incredible speed of 670 million miles per hour. They left stars that actually died long before Earth even came into existence. You may think you understand what big means, but what if everything you believe about size is completely off? We're about to take a journey past neutron stars that spin faster than the blades in your blender, across cosmic strands stretching a billion light years, and into regions where new space is forming faster than light itself can move. If you're ready to have your perspective completely changed about the true scale of existence, stick with me, because what's coming will transform the way you see everything around you. Get ready, we're about to begin. At this very moment, you're standing on a rocky planet moving through space at 67,000 miles per hour. Earth feels enormous to us, mainly because it takes hours to fly across it. The ground under your feet seems solid and permanent. But here's where your sense of scale is about to be shattered. Earth only feels big because of the way we move through it, step by step. Walking from your house to the nearest store feels like a trip. Driving across your state can take half a day. Flying overseas can take an entire day. These experiences trick our brains into thinking Earth is massive. But compared to what's out there in the universe, our planet is smaller than a single speck of dust floating in a giant cathedral. To put this in perspective, if everything in the universe could be scaled down, Earth would disappear from view before you even got past your own cosmic neighborhood. Take the moon, for example. It looks small enough to cover with your thumb, yet it's actually 240,000 miles away. That's like lining up 10 Earths in a row and still not touching it. The truth is, your brain was never built to understand distances this large. Human evolution only prepared us to hunt, gather, and travel through areas measured in miles or kilometers. That's why when we hear numbers like 1,000,000 or 1,000,000,000, our minds treat them almost the same, just really big. But the gap between 1,000,000 and 1,000,000,000 is massive. For example, 1,000,000 seconds equals about 11 and a half days, while 1,000,000,000 seconds equals 32 years. That's the difference we're talking about. Now imagine this. If Earth were the size of a marble, our whole solar system would still be smaller than a single city block. And even then, our solar system is just a tiny speck inside a galaxy that holds 400 billion stars. We're about to step even further. You'll see objects so dense that just a teaspoon of their material would weigh as much as Mount Everest. You'll witness cosmic crashes that release more energy in a single second than our sun will create in 1,000,000 years. You'll encounter structures so enormous that light itself takes longer to cross them than humans have existed on Earth. Everything you thought you knew about size is about to collapse. Suddenly, your house, your city, even your entire country will seem invisible compared to what lies ahead. And believe it or not, in this grand view, Earth itself will still appear larger than some of the things we'll meet next. And while you stand here on Earth, something else is happening that you may never think about. The air around you is constantly pressing down on your body with the weight of an elephant. Every square inch of your skin is under about 14.7 pounds of pressure. You don't notice it because you've lived in this invisible ocean of air since birth. This thin blanket of gas is what allows us to breathe and survive, but it only reaches a few dozen miles above us. Beyond that, at about 62 miles above sea level, the Kármán line, space officially begins. That might sound close until you realize what 62 miles straight up actually means. If you could stack average-sized people on top of each other, you would need 59,520 humans to build a tower reaching the edge of space. Picture that tower of people stretching beyond the clouds, beyond where jets fly, beyond where weather exists. Most commercial airplanes cruise at only 6 to 7 miles high. Even at that altitude, you would die within 15 seconds without pressurization. The air becomes so thin that your blood would literally boil. But you're still only 1/10 of the way to space. Mount Everest, which kills experienced climbers regularly, reaches just 5.5 miles up. You would need to stack 11 Mount Everests to reach space. Here's what makes this distance even more mind-bending. If Earth were shrunk down to the size of a basketball, the atmosphere would be thinner than a sheet of paper wrapped around it. All the air you've ever breathed, every cloud you've ever seen, every bird that's ever flown exists in this impossibly thin shell around our planet. The International Space Station orbits at 250 miles up. Astronauts there are not floating because there's no gravity. Earth's gravity at that altitude is still 89% as strong as it is on the surface. They float because they're falling around Earth at 17,500 miles per hour. They fall continuously but never hit the ground because Earth curves away beneath them. But here's where your perception of distance starts breaking down completely. The space station, which seems impossibly far away, orbits closer to Earth's surface than the distance between New York and Washington, D.C. If you could drive straight up at highway speeds, you could reach the space station in less than 3 hours. Yet, this tiny step away from Earth's surface represents humanity's greatest achievement in space travel. Only about 600 people in all of human history have traveled even this far. The farthest humans have ever traveled is the moon, which is only 3 days away by rocket. But the moon is still trapped in Earth's gravitational embrace. We haven't even begun to escape our planet's influence. And already, the numbers are becoming difficult to imagine. But compared to what comes next, the space station might as well be touching the ground. Light from the sun hits your face 8 minutes and 20 seconds after leaving our star's surface. In those 8 minutes, that light traveled 93 million miles through the vacuum of space. But here's what will melt your brain. In the exact same amount of time, light could circle Earth's equator 7 times. This means something incredible about the sun's size. Our star is so massive that light, the fastest thing in the universe, needs over 4.5 seconds just to travel from one side to the other. Think about that. Light can circle our entire planet in 1/7 of a second, but it needs 4.5 seconds to cross the sun. The sun could swallow over 1 million Earths and still have room left over. The sun contains 99.86% of all the mass in our solar system. Everything else, Earth, Jupiter, Saturn, all the planets, moons, asteroids, and comets combined, makes up just 1/400th of 1%. If the solar system were a giant pizza, the sun would be everything except a few tiny crumbs scattered around the edges. But mass is just one mind-bending aspect of our star. The sun's surface temperature reaches 10,000 degrees Fahrenheit. That's hot enough to vaporize any material known to exist on Earth. However, the surface is actually the coolest part we can observe. The sun's core burns at 27 million degrees. At those temperatures, hydrogen atoms smash together with such violence that they fuse into helium, releasing the energy that keeps you warm. Every second, the sun converts 4 million tons of matter directly into pure energy. This process has been happening for 4 billion years and will continue for another 5 billion years. The amount of energy our star produces in just 1 second could power human civilization for hundreds of thousands of years. Yet, despite this incredible power output, the sun is remarkably average. Astronomers classify it as a yellow dwarf star. In our galaxy alone, there are stars that make our sun look like a birthday candle next to a forest fire. Some stars burn so bright they consume themselves in just a few million years instead of the sun's 10 billion years lifespan. Here's the part that should keep you awake at night. The sun is so far away that it appears as just a tiny disk in our sky. Yet, it's still bright enough to blind you permanently if you stare at it. This average-sized star sitting 93 million miles away completely dominates our planet's energy budget. Without the sun's light, Earth would be a frozen rock with surface temperatures hundreds of degrees below zero. But compared to what comes next, our sun is just a flickering ember. Pluto sits in eternal darkness at the frozen edge of everything you call home. Even though we no longer classify it as a planet, this distant world marks the boundary of the solar system most people imagine. But Pluto is not even close to the real edge. The actual boundary of our solar system stretches so far that it makes the distance to Pluto look like a walk to your mailbox. Pluto orbits our sun at an average distance of 3.7 billion miles. Light from the sun takes over 5 hours to reach this frozen world. From Pluto's surface, the sun appears as just a bright star, providing barely more warmth than starlight. The temperature there never rises above -375 degrees Fahrenheit. Liquid water cannot exist. The atmosphere is so thin, it would be considered a vacuum on Earth. But here's what demolishes your sense of scale. Pluto represents only the inner edge of our solar system's true boundary. Beyond Pluto lies the Kuiper Belt, a ring of icy objects extending another billion miles outward. Beyond that stretches the Oort cloud, a spherical shell of comets that extends halfway to the nearest star. The Oort cloud reaches 50,000 times farther from the Sun than Earth does. If you could somehow shrink our entire solar system down to the size of a grain of sand, the nearest star would still be over a mile away. Picture holding a grain of sand, then walking over a mile to find the next grain of sand that represents the space between stars in our cosmic neighborhood. Most of the universe is this kind of empty space. Our fastest spacecraft, Voyager 1, launched in 1977 and is still traveling away from the Sun at 38,000 miles per hour. After 47 years of continuous flight, it has barely left our solar system. It won't come close to another star for 40,000 years. Even at the speed of light, it would take 4 years and 4 months to reach our nearest stellar neighbor. The space between stars contains almost nothing. In the emptiest regions between star systems, you might find 1 hydrogen atom per cubic foot. Earth's atmosphere contains trillions of atoms in the same space. The vacuum of interstellar space is more perfect than anything we can create in laboratories. This emptiness extends in every direction for distances that would take lifetimes to cross, even at light speed. Our local neighborhood of stars spans dozens of light years. But our local neighborhood is itself just a tiny cluster within something much larger. But compared to what comes next, our entire stellar neighborhood is just getting started. Our galaxy is eating other galaxies right now. As you read this sentence, the Milky Way is slowly devouring smaller galaxy groups, stretching them into streams of stars that wrap around us like cosmic spaghetti. This process has been happening for billions of years, and we're just now beginning to map the stellar graveyards scattered throughout our galactic home. The Milky Way contains between 200 and 400 billion stars. Each one is a sun, potentially hosting its own family of planets. If you could count one star every second, it would take you over 12,000 years to count them all. But the mind-breaking part isn't the number of stars. It's the distance between them. Our galaxy measures 100,000 light years from edge to edge. Light traveling at 670 million miles per hour needs 100,000 years to cross from one side to the other. Voyager 1, humanity's fastest and most distant spacecraft, would need over 1.7 billion years to make the same journey. By the time Voyager crossed our galaxy, the Sun would have burned out, Earth would be gone, and the galaxy itself would have completely changed shape. But here's what makes galactic distances even more incomprehensible. We're not sitting still inside this cosmic structure. Our entire solar system orbits the galactic center at 515,000 miles per hour. At this incredible speed, it still takes us 230 million years to complete one orbit around the galaxy's center. Dinosaurs lived and died during our last quarter orbit. The center of our galaxy hides a supermassive black hole called Sagittarius A star. This monster contains the mass of 4 million suns crushed into a region smaller than Mercury's orbit. Stars near the galactic center orbit this black hole so fast they complete full orbits in just 16 years. These stars experience gravitational forces so extreme that time itself runs slower for them compared to us. From our position in the galaxy's suburbs, we cannot see the center due to massive clouds of dust and gas. If you could remove all the dust, the galactic center would appear in our night sky as bright as the full moon. The sky would glow with the light of billions of ancient stars packed into a region smaller than the constellation Orion. Our solar system sits about 26,000 light years from the galactic center, roughly halfway to the edge. We live in what astronomers call the Orion Arm, a minor spiral arm containing just a tiny fraction of the galaxy's stars. Most of the Milky Way's mass exists in regions we will never visit. But compared to what comes next, our galaxy is just one small island in an infinite ocean. A star named Uy Scuti is so large that if you placed it where our sun sits, It would swallow Mercury, Venus, Earth, Mars, and extend past Jupiter's orbit. Light would need 9 hours to travel around this monster's circumference. If you could somehow drive around Uy-Scuti's equator at highway speeds, the journey would take you 9 million years to complete. Uy-Scuti belongs to a class of stars called red supergiants. These stellar monsters represent the final phase of the most massive stars' lives. When a star contains more than 25 times our Sun's mass, it burns through its nuclear fuel at an incredible rate. The more massive the star, the shorter and more spectacular its life becomes. While our Sun will burn steadily for 10 billion years, Uy-Scuti will exist for only about 10 million years total. It burns hydrogen fuel so rapidly that it's already in its death phase. Despite being relatively young, the star's outer layers have expanded to tremendous size as the core struggles to maintain nuclear fusion against its own crushing gravity. Here's what makes Uy-Scuti truly mind-bending. Despite being 1.7 billion times larger than our Sun in volume, it only contains about 30 times more mass. This means the star is incredibly diffuse. Its outer atmosphere is so thin that it's essentially a vacuum by Earth standards. If you could somehow stand on a platform within Uy-Scuti's outer layers, you might not realize you were inside a star. But Uy-Scuti is not even close to being the most massive star we know. That title belongs to stars in the R136 cluster located 65,000 light-years away. These monsters contain up to 300 times our Sun's mass packed into much smaller volumes. They burn so hot and bright that they blast their outer layers into space with stellar winds moving at thousands of miles per second. The most massive stars we can observe push against theoretical limits for stellar formation. Above a certain mass, a star becomes so hot that radiation pressure prevents it from accumulating more material. These stellar giants burn through their fuel so quickly that they exist for only a few million years before exploding as hypernovas. Explosions so violent, they can be seen across billions of light years. When Uy-Scuti finally dies, it will likely explode as a supernova visible during daytime on Earth. Despite being thousands of light years away, the explosion will outshine our entire galaxy for several weeks. The blast will create and scatter elements heavier than iron throughout space, seeding future generations of stars and planets. But compared to what comes next, even these stellar monsters are surprisingly delicate. A neutron star called PSRJ 1748-2446 AD rotates 716 times per second. In the time it takes you to blink once, this stellar corpse completes over 200 full rotations. Its equator moves at nearly 100 million miles per hour. Any faster and centrifugal force would tear the star apart. Neutron stars represent what happens when a massive star's core collapses under its own gravity. In less than 1 second, a region the size of Earth gets crushed down to a sphere just 12 miles across. The collapse is so violent that protons and electrons get smashed together to form neutrons. What remains is the densest matter in the known universe. A neutron star contains more mass than our Sun, compressed into a volume smaller than Manhattan. The gravitational field at its surface is 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star's surface, you would weigh the same as Mount Everest. The escape velocity from a neutron star is 100,000 miles per second, nearly half the speed of light. But the density is what truly breaks your brain. 1 teaspoon of neutron star material would weigh 6 billion tons on Earth. That's more than all the cars, trucks, and buses on the planet combined, compressed into something you could hold in your hand. A sugar cube of this material would weigh as much as a mountain. The magnetic field around a neutron star is 1 trillion times stronger than Earth's magnetic field. This intense magnetism funnels charged particles along the magnetic poles, creating beams of radiation that sweep through space like lighthouse beams. When these beams point toward Earth, we detect regular pulses of radio waves. That's why we call them pulsars. Some neutron stars are even more extreme. Magnetars have magnetic fields 1,000 times stronger than regular neutron stars. These magnetic fields are so intense they would erase every credit card on Earth from a distance of 100,000 miles. The magnetic field energy of a magnetar could power human civilization for 1 billion years. Neutron stars are incredibly long-lived. While massive stars burn out in millions of years, neutron stars can spin for billions of years with atomic precision. The most stable pulsars keep time more accurately than the best atomic clocks humans have built. Astronomers use pulsar timing to detect gravitational waves and navigate spacecraft. When two neutron stars spiral into each other, they create kilonova explosions that forge gold, platinum, and uranium. Every gold ring, every platinum catalyst, every uranium atom on Earth was created inside these cosmic collisions billions of years ago. But compared to what comes next, neutron stars seem almost familiar. Drop a marshmallow onto a neutron star, and it would impact the surface with the explosive force of 1,000 hydrogen bombs. NASA calculated this scenario to demonstrate the ridiculous gravitational field surrounding these stellar remnants. The marshmallow would accelerate to millions of miles per hour before striking the neutron star's crystalline iron surface. The surface of a neutron star is the smoothest place in the universe. Any mountain on a neutron star would be limited to about 1/10 of an inch in height before the intense gravity crushed it flat. The surface gravity is so strong that it warps space and time. Light climbing out of a neutron star's gravity loses energy, becoming redder and dimmer by the time it reaches Earth. Neutron star surfaces experience starquakes that make Earth's most powerful earthquakes seem like gentle tremors. When the neutron star's crust shifts by just a fraction of an inch, it releases more energy than Earth's sun produces in 100,000 years. These starquakes can change the star's rotation rate in milliseconds, causing pulsar glitches that astronomers can detect from thousands of light years away. But the real violence happens when matter falls onto a neutron star from a companion star. Gas spiraling inward forms an accretion disk that heats to millions of degrees. When enough material accumulates on the surface, nuclear fusion ignites in a thermonuclear explosion that can be seen from across the galaxy. These X-ray bursts release more energy in seconds than our sun produces in weeks. Some neutron stars strip matter from companion stars so efficiently that they become recycled pulsars. The infalling matter spins up the neutron star like a cosmic gyroscope, causing it to rotate hundreds of times per second. These millisecond pulsars are among the most precise timekeepers in the universe, maintaining their rotation rates to within nanoseconds over decades. The magnetic fields around neutron stars create phenomena that have no equivalent anywhere else in the universe. Near the magnetic poles, electrons accelerate to nearly light speed, creating beams of gamma rays so intense they could kill every living thing on Earth from 1,000 light years away. When these death beams sweep across space, they create the lighthouse effect that allows us to detect pulsars. Neutron stars also demonstrate Einstein's general relativity in ways impossible to study anywhere else. Time runs slower in their intense gravitational fields. Light gets bent around them, allowing us to see parts of their backside. Their rotation drags space and time around with them in an effect called frame dragging. But compared to what comes next, even neutron stars follow predictable rules. Binary neutron star systems are cosmic vampires that slowly devour each other over millions of years. When two neutron stars orbit close together, they create gravitational waves that carry energy away from the system. This energy loss causes the stars to spiral closer and closer together in a deadly dance that can only end in collision. The most famous binary neutron star system, called the Hulse-Taylor binary, provided the first indirect proof of gravitational waves decades before LIGO detected them directly. The two neutron stars in this system orbit each other every 7.75 hours. Each orbit they lose energy to gravitational waves and move 17 feet closer together. In about 300 million years they will collide. But some neutron stars don't wait for collision to steal from their neighbors. When a neutron star has a normal companion star, it can pull material from the companion's outer layers. This stolen gas forms a glowing accretion disk that spirals into the neutron star at millions of miles per hour. The friction in this disk heats the gas to temperatures of 100 million degrees. These accreting neutron stars become X-ray sources so bright they outshine entire galaxies. The infalling matter releases gravitational energy more efficiently than nuclear fusion. When gas hits the neutron star's surface, it's moving at thousands of miles/s and carries kinetic energy equivalent to nuclear weapons. The impact creates X-ray bursts that can temporarily increase the system's brightness by factors of millions. Some binary systems create even stranger phenomena. Black widow pulsars are neutron stars that slowly evaporate their companion stars with intense radiation. The pulsar's energetic particles strip away the companion's outer layers, creating a glowing cloud of gas around the system. Eventually, the companion star will be completely consumed, leaving behind an isolated pulsar. Redback spiders represent another class of cosmic cannibals. These are neutron stars with companion stars massive enough to survive the pulsar's radiation, but still small enough to lose material to their dense partner. The interaction creates complex patterns of X-ray emission as material flows between the stars. The most violent binary interactions occur when two neutron stars finally merge. The collision creates a kilonova explosion that synthesizes heavy elements and ejects them into space at thousands of miles/s. These mergers are responsible for creating most of the gold, platinum, and rare earth elements in the universe. But compared to what comes next, stellar cannibalism is just an appetizer. On August 17, 2017, gravitational wave detectors felt space itself vibrate as two neutron stars collided 130 million light-years away. The merger, designated GW170817, lasted just 100 seconds, but released more energy than our Sun will produce in its entire 10 billion-year lifetime. The collision created an explosion called a kilonova that was visible to amateur astronomers despite occurring in another galaxy. For several days, this single event outshone all the stars in its host galaxy combined. But the light show was just a byproduct of something far more significant happening at the subatomic level. When two neutron stars merge, they create conditions that exist nowhere else in the universe. Temperatures reach 100 billion degrees. Densities exceed that of atomic nuclei. Neutrons get crammed together so tightly that they form elements heavier than iron through rapid neutron capture. This process, called the R process, creates gold, platinum, uranium, and dozens of other heavy elements in just seconds. The collision ejected roughly 50 Earth masses of pure heavy elements into space at thousands of miles/s. This single event created more gold than exists in Earth's entire crust. The platinum in your jewelry, the gold in your electronics, the uranium powering nuclear reactors, all of it was forged in stellar collisions like this 1 billion years ago. But neutron star mergers don't just create elements. They also provide crucial tests of fundamental physics. The collision generated gravitational waves that traveled across 130 million light-years without losing their information content. These waves confirmed Einstein's predictions about how space and time behave under the most extreme conditions. The merger also produced a short gamma-ray burst, one of the most energetic explosions in the universe. For just 2 seconds, this burst released more energy in gamma rays than our Sun produces in visible light over millions of years. If a similar burst occurred within a few thousand light-years of Earth, it could strip away our ozone layer and cause mass extinctions. Scientists estimate that neutron-star mergers occur roughly once per year in a galaxy the size of the Milky Way. Over cosmic time, these collisions have enriched the universe with heavy elements necessary for rocky planets and complex chemistry. Without neutron-star mergers, the universe would contain only hydrogen, helium, and lithium. The gravitational waves from GW 170817 also provided a new way to measure the expansion rate of the universe. By combining gravitational wave data with optical observations, astronomers calculated the Hubble constant with unprecedented precision. But compared to what comes next, neutron-star collisions are just the beginning of cosmic violence. Dark matter outweighs all the stars, planets, gas, and dust in the universe by a ratio of 5 to 1. Every atom in your body, every grain of sand on Earth, every star in the night sky, represents just 16% of all matter that exists. The other 84% is completely invisible and interacts with ordinary matter only through gravity. We know dark matter exists because we can see its gravitational effects on everything else. Galaxies rotate too fast to hold together based on the visible matter alone. Galaxy clusters move in ways that require 5 times more mass than we can observe. Gravitational lensing bends light around massive objects in patterns that demand invisible matter. But here's what makes dark matter so mysterious. It passes through ordinary matter as if it doesn't exist. Right now, billions of dark matter particles are streaming through your body every second without interacting with a single atom. Dark matter particles might be colliding inside you constantly, but they leave no trace of their passage. Scientists have built detectors deep underground, shielded by miles of rock, hoping to catch dark matter particles in the act of occasionally bumping into normal atoms. These experiments require isolation from cosmic rays and radioactive contamination. Because dark matter interactions are so rare and weak, after decades of searching with increasingly sensitive equipment, we still haven't directly detected a single dark matter particle. The leading theory suggests dark matter consists of particles called WIMPs, weakly interacting massive particles. These hypothetical particles were created in the first moments after the Big Bang, but have completely different properties from ordinary matter. They don't emit light, don't absorb light, and don't interact electromagnetically. Alternative theories propose that dark matter might be primordial black holes formed in the early universe, or axions, or sterile neutrinos, or something even stranger that we haven't imagined yet. Some scientists question whether dark matter exists at all, suggesting instead that our understanding of gravity needs modification on cosmic scales. What we do know is that dark matter played a crucial role in structure formation. In the early universe, dark matter began clumping together first because it didn't interact with radiation. These dark matter clumps provided gravitational scaffolding that allowed ordinary matter to collect and form the first stars and galaxies. Computer simulations show that dark matter forms a cosmic web of filaments and nodes throughout the universe. Galaxies form where ordinary matter falls into dark matter halos. The Milky Way sits inside a dark matter halo extending far beyond the visible galaxy. But compared to what comes next, dark matter is just the supporting framework for an even stranger cosmic component. The Milky Way is trapped inside a spherical prison made of dark matter that extends 3 times farther than our galaxy's visible edge. This invisible halo contains 10 times more mass than all the stars, gas, and dust we can observe. Without this dark matter cage, our galaxy would have flown apart billions of years ago. Our galaxy rotates like a cosmic pinwheel, but the rotation doesn't follow the rules of normal physics. Based on the visible matter alone, the outer stars should orbit much slower than the inner stars, just like planets in our solar system. Instead, stars throughout the galaxy's disk all orbit at roughly the same speed of about 500,000 miles per hour. This flat rotation curve was one of the first major pieces of evidence for dark matter. Astronomer Vera Rubin discovered in the 1970s that galaxy after galaxy showed the same impossible rotation pattern. The only explanation was invisible matter providing additional gravitational pull to keep the outer stars moving so fast. Dark matter halos extend much farther than the galaxies they contain. The Milky Way's dark matter halo reaches out roughly 300,000 light-years from the galactic center. For comparison, the visible galaxy is only 100,000 light-years across. We live inside this vast, invisible structure that shapes everything about our cosmic environment. The dark matter halo surrounding our galaxy isn't smooth or evenly spread out. Simulations done on powerful computers show that it's full of smaller clumps, known as substructures, which were left behind during its early formation. Some of these subhalos may even hold tiny galaxies of their own, while others remain completely dark, seen only through the pull of their gravity. As the Milky Way travels through space, it's constantly gathering dark matter from its surroundings. In a way, our galaxy acts like a collector, drawing in both individual particles and entire dark matter clumps. This process has been going on for more than 13 billion years, slowly adding to the invisible mass that shapes and supports our galaxy today. The local group of galaxies, which includes the Milky Way and Andromeda, exists within an even larger dark matter structure called the local supercluster. This structure spans over 100 million light-years and contains the mass equivalent of 10,000 trillion suns, most of it in dark matter. Dark matter also influences star formation within our galaxy. The gravitational pull from dark matter clumps can trigger the collapse of gas clouds, leading to bursts of star formation. The distribution of dark matter throughout the galaxy affects where and when new stars are born. But compared to what comes next, dark matter is a passive player in an even more dramatic cosmic story. Dark energy is ripping the universe apart at an accelerating rate. This mysterious force makes up 68% of everything that exists. Yet, we have no idea what it actually is. Dark energy acts like anti-gravity, pushing space itself to expand faster and faster over time. 5 billion years ago, dark energy overcame gravity and began accelerating the expansion of the universe. Before this cosmic transition, gravity was winning the battle, slowing down the expansion left over from the Big Bang. Now, dark energy dominates, and the expansion rate increases every day. The universe will expand forever, growing colder and more empty with each passing billion years. On small scales, dark energy has no effect. Gravity easily overpowers dark energy within galaxies, star systems, and planetary systems. Your body, Earth, and even our entire galaxy are gravitationally bound strongly enough to resist dark energy's expansion. But on larger scales, dark energy rules everything. Galaxy clusters represent the largest structures that gravity can hold together against dark energy. Clusters containing thousands of galaxies span tens of millions of light-years and contain the mass of millions of billions of suns. Even these massive structures are now being stretched apart by accelerating expansion. The local group containing the Milky Way and Andromeda galaxies will remain gravitationally bound forever. In about 4 billion years, these two galaxies will merge into one giant elliptical galaxy. But most other galaxies are already moving away from us faster than we could ever reach them, even traveling at light speed. Currently, we can observe galaxies up to about 46 billion light-years away. But dark energy ensures that this cosmic horizon will shrink over time. Galaxies at the edge of our observable universe are moving away from us faster than light speed. Eventually, even nearby galaxy groups will disappear beyond our cosmic horizon. In the far future, dark energy will create a lonely universe. Each gravitationally bound galaxy group will become isolated in its own expanding bubble of space. Stars will burn out, black holes will evaporate, and the universe will approach maximum entropy. Dark energy will continue pushing empty space apart until the universe becomes a cold, dark void. Scientists have proposed several theories for dark energy's nature. It might be vacuum energy, quantum fluctuations in empty space, or a dynamic field called quintessence. Some theories suggest dark energy strength might change over time, leading to even more dramatic cosmic evolution. But compared to what comes next, dark energy is just setting the stage for cosmic objects that challenge everything we thought we knew about physics. A supermassive black hole called 3C273 blazes with the light of 1,000 Milky Way galaxies. Despite being smaller than our solar system, this monster sits at the heart of a distant galaxy, consuming stars and gas at such a furious rate that it outshines every other object in its cosmic neighborhood. The energy it releases in 1 second equals what our sun produces in 10 million years. Quasars represent supermassive black holes in their most violent feeding phase. When galaxies collide or merge, enormous amounts of gas get funneled into the central black hole. This material forms a superheated accretion disk that glows brighter than anything else in the universe. The disk reaches temperatures of billions of degrees, hot enough to strip electrons from atoms and create a plasma more energetic than the core of any star. But here's what makes quasars truly mind-breaking. They achieve this incredible luminosity through pure gravitational energy. As matter spirals into a black hole, gravity accelerates it to nearly light speed. The conversion of gravitational potential energy to heat and light is far more efficient than nuclear fusion. While stars convert less than 1% of their mass to energy, black holes can convert over 30%. The most luminous quasar we've discovered, designated J0905-0014, shines with the brightness of 40 trillion suns. This single object, powered by a black hole 20 billion times more massive than our sun, releases more energy every second than 400 billion stars combined. It's so bright that we can see it from over 12 billion light-years away. Quasars also launch jets of material at 99.9% the speed of light. These jets extend for millions of light-years beyond the host galaxy, creating radio emissions detectable across cosmic distances. The magnetic fields channeling these jets are stronger than anything we can create on Earth. Yet they maintain their focus across distances larger than galaxy clusters. Most quasars existed when the universe was young and galaxies were smaller, closer together, and more likely to interact. In the early universe, galaxy mergers happened frequently, providing abundant fuel for supermassive black holes. Today's universe is more spread out, so quasars are much rarer. The Milky Way's central black hole is currently starving, consuming less material than a typical asteroid every year. When a quasar finally exhausts its fuel supply, it fades to become an ordinary galaxy with a dormant supermassive black hole at its center. Every large galaxy we observe today likely went through a quasar phase billions of years ago. The supermassive black hole in our galaxy's center represents what's left after our own quasar era ended. But compared to what comes next, even these cosmic lighthouses are just nearby neighbors. The nearest known quasar sits 3.2 billion light-years away from Earth. Even if you could travel at the speed of light, the journey would take 3.2 billion years. But the universe is only 13.8 billion years old. This means you could have started your journey when the first stars were forming, and you still wouldn't be halfway there. This distance represents something profound about the structure of space and time. When we observe this quasar, we're seeing it as it existed 3.2 billion years ago when Earth was still a young planet with only primitive life. The light we detect today left that quasar before complex life evolved in our oceans. But most quasars lie much farther away. The most distant quasar discovered, J0313-1806, existed when the universe was only 670 million years old. Its light has been traveling toward us for over 13 billion years. This quasar was shining when the first galaxies were just beginning to form from primordial gas clouds. Here's what makes these distances even more staggering. Space itself has been expanding while the light traveled toward us. When that distant quasar emitted the light we see today, it was much closer to our location. But cosmic expansion has carried it away from us during the light travel time. Today, that same quasar is over 46 billion light-years away from us. At such vast distances, we're not just looking far into space. We're looking far back in time. Astronomy becomes archaeology when we study the most distant objects. Every quasar observation provides a snapshot of cosmic conditions billions of years in the past. We're literally seeing the universe grow up before our eyes. The light from distant quasars also gets stretched by cosmic expansion during its journey. This stretching, called cosmological redshift, makes the light redder and dimmer by the time it reaches Earth. Some quasar light has been stretched so much that ultraviolet radiation becomes infrared by the time we detect it. Studying quasars at different distances allows astronomers to map cosmic evolution. We can observe how supermassive black holes grew over time, how galaxy formation progressed, and how the universe's expansion rate has changed. Each quasar acts like a time machine, preserving information about cosmic conditions from its era. The most distant quasars required the universe's most powerful telescopes to detect. The Hubble Space Telescope can barely resolve them as point sources. The James Webb Space Telescope, with its larger mirror and infrared capabilities, is discovering even more distant quasars that formed when the universe was just a few 100 million years old. But compared to what comes next, these individual beacons are just street lights in a cosmic city we're only beginning to map. Quasar J0313-1806 is visible from a distance of 46 billion light-years. This cosmic lighthouse has been beaming energy across space for over 13 billion years, and its light is still bright enough to trigger individual photons in our most sensitive telescopes. If this quasar were located at the center of our solar system, it would appear brighter than the Sun despite being a point source. But the true power of quasars lies in their ability to illuminate the universe's large-scale structure. As quasar light travels across cosmic distances, it passes through clouds of gas and dust that leave absorption fingerprints in the spectrum. These absorption lines map the distribution of matter throughout the universe like a cosmic barcode. The Lyman alpha forest represents one of astronomy's most important tools for mapping the early universe. When quasar light passes through hydrogen clouds, it creates a series of absorption lines that look like a forest of vertical lines in the spectrum. Each line represents a cloud of gas between us and the quasar. By studying thousands of quasar spectra, astronomers can map how matter was distributed when the universe was young. Quasars also serve as cosmic flashlights for detecting invisible matter. When a quasar's light passes near a massive object, gravitational lensing bends the light and creates multiple images of the same quasar. These gravitational lens systems allow us to weigh galaxy clusters and study dark matter distributions. Some quasars appear as perfect rings of light called Einstein rings. When the alignment is exact, the most powerful quasars can ionize hydrogen across distances of hundreds of millions of light-years. During the early universe, quasars played a crucial role in the epoch of reionization when the first stars and black holes heated the universe's neutral hydrogen back into a plasma state. This process determined how the first galaxies could form and evolve. Blazars represent the most extreme class of quasars where one of the relativistic jets points directly toward Earth. These objects can vary in brightness by factors of hundreds in just days or weeks. When a blazar flares, it can temporarily become the brightest object in the gamma-ray sky, outshining everything else in that energy band. Radio telescopes can detect quasar jets across even greater distances than optical telescopes can see the central engine. Some quasar jets remain collimated across distances of millions of light years, maintaining their narrow focus despite traveling through intergalactic space. The physics behind this collimation still puzzles astrophysicists. Quasars have also provided some of the most precise tests of Einstein's general relativity. The orbits of stars around the supermassive black holes powering quasars experience time dilation and gravitational redshift exactly as Einstein predicted. Some quasar systems show periodic variations caused by relativistic effects in the accretion disk. But compared to what comes next, even these cosmic beacons are just individual stars in a web that spans the entire universe. The vacuum of space contains enough dark energy to outweigh every star, planet, gas cloud, and black hole in the observable universe by more than 2 to 1. This invisible energy fills every cubic inch of empty space and drives the accelerating expansion that will ultimately determine the fate of everything that exists. Dark energy makes up 68% of the universe's total mass energy content. All the matter we can see, stars, galaxies, gas, and dust, represents just 5% of the cosmic inventory. Even adding dark matter only brings the total matter content to 32%. The majority of our universe consists of something we can't see, can't touch, and barely understand. But here's what makes dark energy so fundamentally different from matter. It doesn't clump or cluster. While matter forms stars, planets, and galaxies through gravitational attraction, dark energy remains perfectly uniform throughout space. Every cubic meter of empty space contains exactly the same amount of dark energy as every other cubic meter. Regardless of location, the energy density of dark energy is incredibly small by everyday standards. Each cubic meter of empty space contains only about 6 hydrogen atoms worth of dark energy. But when you multiply this tiny density by the vast volume of space, the total energy becomes enormous. The observable universe contains 10 to the 87th cubic meters of space, making dark energy the dominant component of cosmic reality. Dark energy acts like a cosmological constant, providing a repulsive force that counteracts gravity on large scales. Einstein originally introduced this concept to explain a static universe, then called it his greatest blunder when Hubble discovered cosmic expansion. Now, we know Einstein was accidentally correct. The universe does contain a cosmological constant, but it causes acceleration rather than static equilibrium. The acceleration caused by dark energy began dominating cosmic evolution about 5 billion years ago. Before this transition, gravity was slowing down the expansion left over from the Big Bang. Since dark energy took over, the expansion rate has been increasing steadily. This acceleration determines which galaxy clusters represent the largest structures that will ever form. Current observations suggest dark energy strength has remained constant throughout cosmic history. If this continues, the universe will expand exponentially in the far future. Galaxies beyond our local group will eventually disappear beyond our cosmic horizon. Stars will burn out, black holes will evaporate, and the universe will approach maximum entropy. Alternative theories suggest dark energy might be dynamic rather than constant. Quintessence models propose that dark energy strength could change over time, leading to different cosmic futures. Some theories even suggest dark energy could reverse direction, causing the universe to contract in a big crunch. But compared to what comes next, dark energy is just the backdrop against which the largest structures in the universe have formed. The local group of galaxies spans 10 million light-years and contains over 80 individual galaxies. Yet it occupies less than 1% of the space inside a typical cosmic void. These voids represent the largest structures in the universe, regions where dark energy has pushed matter apart so effectively that galaxies become rare islands scattered across vast emptiness. Cosmic voids contain less than 1/10 the average density of matter found elsewhere in the universe. The largest known void, the Boötes void, spans 330 million light-years across and contains almost no galaxies. If the Milky Way were located in the center of this void, we wouldn't have discovered other galaxies until the 1990s, completely changing our understanding of cosmic history. But voids aren't completely empty. They contain a sparse network of gas filaments and the occasional dwarf galaxy. The galaxies that do exist in voids often show unusual properties. They tend to be smaller, bluer, and more actively forming stars than galaxies in denser regions. The isolation allows them to evolve differently from galaxies embedded in rich clusters. The boundaries of voids are defined by sheets and filaments of galaxies that form the cosmic web. These structures contain most of the universe's ordinary matter, organized into networks that span hundreds of millions of light-years. Galaxy clusters form where multiple filaments intersect, creating the nodes of this cosmic web. Our local group sits within a filament connecting the Virgo cluster to the Fornax cluster. This cosmic filament is part of a larger structure called the local supercluster, which spans 110 million light-years. But even this enormous structure represents just a tiny fraction of the cosmic web's total extent. The cosmic web emerged from tiny density fluctuations in the early universe. Dark matter began clumping first because it didn't interact with radiation. Ordinary matter later fell into the gravitational wells created by dark matter, forming the first stars and galaxies along these cosmic filaments. Computer simulations reveal that the cosmic web has a hierarchical structure. Smaller filaments connect to larger ones, which connect to even larger sheets and walls. The largest walls, like the Sloan Great Wall, extend over 1 billion light-years across. These represent some of the largest coherent structures that can exist in our expanding universe. The distribution of matter in the cosmic web follows mathematical patterns similar to soap bubbles or neural networks. Large voids are surrounded by thin walls of matter with dense nodes where walls intersect. This structure gives the universe a foamy appearance when viewed on the largest scales. But compared to what comes next, even these cosmic webs are just the framework for structures that challenge our understanding of how large things can grow. Cosmic filaments stretch across hundreds of millions of light-years, forming the largest structural elements in the universe. These threads of dark matter and gas connect galaxy clusters like a vast three-dimensional web. The filament containing our local group extends over 500 million light-years. Yet, it's just one strand in a network that spans the entire observable universe. Individual filaments can contain the mass equivalent of 10 trillion suns stretched across distances that would take light hundreds of millions of years to traverse. Despite their enormous size, filaments are surprisingly thin, typically only a few million light-years wide. This creates structures with aspect ratios more extreme than human hair compared to its length. But here's what makes cosmic filaments so crucial. They're the highways along which galaxies travel and grow. Matter flows along these structures from low-density regions toward high-density nodes where galaxy clusters form. This cosmic traffic system has been operating for over 13 billion years, continuously feeding matter to the largest gravitational structures. The Pisces-Cetus supercluster complex represents one of the largest filament structures we can observe. This cosmic thread spans over 1 billion light-years and contains thousands of galaxy groups arranged in a roughly linear pattern. Our local group lies near one end of this structure, giving us a sideways view of its enormous extent. Recent observations have detected the gas content of cosmic filaments directly for the first time. X-ray telescopes found million-degree plasma filling the space between galaxy clusters, confirming theoretical predictions about the cosmic web's hot gas content. This plasma contains more than half of all ordinary matter in the universe, hidden in the near vacuum between galaxies. Cosmic filaments also channel dark matter flows on scales impossible to observe directly. Computer simulations show dark matter streaming along these structures at thousands of kilometers per second. When these dark matter flows converge at filament intersections, they create the most massive galaxy clusters in the universe. The formation of cosmic filaments began during the first few 100 million years after the Big Bang. Tiny quantum fluctuations in the early universe provided the seeds that grew into today's cosmic web. The pattern we observe today preserves information about conditions when the universe was less than 1% of its current age. Some filaments contain surprising substructures. The Perseus-Pisces chain includes multiple galaxy clusters connected by bridges of galaxies and gas. These bridges demonstrate how cosmic filaments can contain complex internal organization rather than simple linear arrangements. But compared to what comes next, even these cosmic highways are just the infrastructure supporting the largest individual objects that exist. The Hercules Corona Borealis Great Wall stretches 10 billion light-years across space, making it the largest known structure in the observable universe. This cosmic wall contains billions of galaxies arranged in a roughly flat sheet that would take light 10 billion years to cross from one end to the other. Yet, even this monster represents just a tiny fraction of the observable universe's total volume. Superclusters like Laniakea, which contains our local group, span 500 million light-years across and contain the mass of 100,000 trillion suns. But Laniakea is just one of millions of superclusters scattered throughout observable space. The supercluster containing our entire cosmic neighborhood would appear as just as small when viewed on the scale of the Great Wall. But here's what breaks your brain about these scales. The Hercules Corona Borealis Great Wall is so large that it challenges our understanding of cosmic structure formation. Theoretical models predict that structures this large should not exist because there hasn't been enough time since the Big Bang for gravity to assemble them. The wall's existence suggests our models of cosmic evolution are incomplete. The Great Wall consists of gamma-ray bursts and galaxy clusters arranged in a pattern that persists across billions of light-years. These gamma-ray bursts mark the locations of massive star deaths and black hole formations, tracing out the underlying distribution of matter. The statistical analysis required to detect this structure involved mapping thousands of cosmic explosions across vast distances. Even more mysterious structures have been proposed, but remain controversial. The cold spot in the cosmic microwave background might represent a supervoid 18 billion light-years across. If confirmed, this would be an absence of matter on scales that dwarf even the Great Wall. The spot appears as a slightly cooler region in the radiation left over from the Big Bang. Other candidate megastructures include the Sloan Great Wall at 1.37 billion light-years across, and the South Pole Wall, discovered in 2019 spanning 1.4 billion light-years. Each discovery pushes the boundaries of what we thought possible for cosmic structure formation. The existence of such large structures also constrains theories about dark energy and cosmic inflation. If dark energy has been constant throughout cosmic history, structures above a certain size should be impossible to form. The Great Wall and similar structures provide tests of fundamental physics on scales unavailable in any laboratory. These structures also raise questions about the homogeneity principle, the assumption that the universe looks the same in all directions when viewed on large enough scales. Structures spanning significant fractions of the observable universe challenge this fundamental assumption of cosmology. But compared to what comes next, even these record-breaking structures are just patterns within something far stranger. If the universe is finite and curved back on itself, we might be observing the same cosmic objects multiple times without realizing it. Light from a single galaxy could travel around the universe's curvature and reach us from different directions, creating duplicate images separated by billions of years in time. This means some of the galaxies in our deepest sky surveys might be the same object photographed at different ages. The cosmic microwave background provides our strongest constraint on the universe's overall shape and size. Analysis of temperature fluctuations in this ancient radiation suggests the universe is either infinite or much larger than the observable region. But if the universe is finite, it must be at least 250 times larger than what we can observe. But here's what makes a finite universe so mind-bending. It would create a cosmic hall of mirrors effect. Every object would produce multiple images scattered across the sky, each showing the object at a different stage of its evolution. A galaxy might appear young and blue in one direction, while simultaneously appearing old and red in another direction, representing the same object billions of years later. Detecting these duplicate images requires sophisticated statistical analysis. Researchers look for correlations in galaxy positions and properties that would indicate multiple views of the same cosmic structures. The challenge lies in accounting for cosmic evolution. The same galaxy viewed after billions of years of additional evolution might look completely different. Some studies have claimed to find evidence for cosmic duplication in galaxy surveys and the cosmic microwave background. These analyses suggest possible repeating patterns on scales approaching the size of the observable universe. However, other researchers dispute these findings, arguing that the patterns could arise from random statistical fluctuations. The search for cosmic topology extends beyond galaxy surveys. Gravitational wave detectors might eventually detect the same cosmic collision from multiple directions if the universe wraps around on itself. This would provide the most direct proof of cosmic duplication ever observed. Different topologies would create different signature patterns. A universe that wraps around like a three-dimensional torus would produce one pattern of duplicated images. A universe curved like a three-dimensional sphere would create a different pattern. The specific topology determines how many duplicate images we should expect and where they should appear. The implications of a finite universe are profound for physics and philosophy. It would mean the universe contains only a finite amount of matter and energy, contradicting some interpretations of quantum mechanics that require infinite space for certain processes. But compared to what comes next, the question of cosmic topology is just one puzzle piece in understanding the true boundary of everything we can ever observe. The cosmic microwave background represents the farthest edge of the observable universe, a glowing shell of ancient light that marks the moment when atoms first formed and the universe became transparent. This radiation has been traveling toward us for 13.8 billion years, carrying information from when the universe was only 380,000 years old and 1,000 times smaller than it is today. Before this moment, the universe was opaque. Free electrons scattered photons so efficiently that light could only travel microscopic distances before being absorbed and re-emitted. The entire cosmos glowed with the intense heat of creation, but no light could escape to travel across space. We can never observe anything from before this epoch with electromagnetic radiation. But here's what makes the cosmic microwave background so remarkable. It provides a baby picture of the entire universe when it was smooth and nearly uniform. The tiny temperature variations we observe, just a few millionths of a degree, represent the seeds that would eventually grow into galaxies, stars, and planets. Every structure we see today began as microscopic ripples in this ancient light. The surface of last scattering, where this radiation originated, now lies 46 billion light-years away from us due to cosmic expansion. The atoms that emitted this light have since been incorporated into billions of generations of stars and galaxies. Some of the hydrogen that created the cosmic microwave background might now exist in your body. This ancient radiation fills the entire universe uniformly. Every cubic inch of empty space contains about 400 cosmic microwave background photons left over from the Big Bang. These photons have been redshifted by cosmic expansion from visible light to microwave frequencies. What once blazed with the intensity of the sun's surface now appears as a faint radio glow. The cosmic microwave background is nearly perfect in its uniformity, varying in temperature by only 1 part in 100,000 across the entire sky. This incredible smoothness creates the horizon problem. Regions that should never have been in contact appear to have the same temperature. Cosmic inflation theory solves this puzzle by proposing that all observable space was once smaller than a subatomic particle. Precision measurements of this background radiation have determined fundamental cosmic parameters with unprecedented accuracy. We know the universe's age, density, composition, and geometry from studying the statistical properties of these ancient photons. The cosmic microwave background has become the Rosetta Stone of cosmology. But compared to what comes next, this ultimate boundary of observation is just the beginning of cosmic mysteries that extend far beyond what we can ever see. Cosmic microwave background photons have been traveling through space for 13.7 billion years. But they didn't begin their journey at the Big Bang. These photons were created when the universe cooled enough for electrons to combine with protons and form the first neutral hydrogen atoms. Before this recombination event, the universe was a hot, dense plasma that trapped all electromagnetic radiation. The moment of recombination happened everywhere in space simultaneously when the universe reached a temperature of about 3,000 degrees. At this critical point, electrons could finally bind to atomic nuclei without being immediately knocked free by energetic photons. The universe suddenly became transparent, and light could travel freely for the first time. But here's what makes this ancient light so extraordinary. It carries a perfect record of cosmic conditions from that pivotal moment. Every photon in the cosmic microwave background preserves information about the density, temperature, and composition of the primordial universe. These photons are the oldest light in existence, older than any star or galaxy. The original light was emitted at a temperature matching the surface of the sun, glowing bright orange-red across the entire sky. But cosmic expansion has stretched these photons during their journey, redshifting them from visible light down to microwave frequencies. The radiation that once blazed with stellar intensity now appears as faint radio waves detectable only with sensitive instruments. Modern telescopes can map this background radiation with extraordinary precision. The Planck satellite measured temperature variations across the entire sky with an accuracy of millionths of a degree. These tiny fluctuations represent quantum fluctuations from the inflationary epoch stretched to cosmic scales by the rapid expansion of space. The polarization patterns in cosmic microwave background radiation provide additional information about the early universe. These patterns preserve evidence of gravitational waves from cosmic inflation, sound waves traveling through the primordial plasma, and magnetic fields present during recombination. The cosmic microwave background also serves as a backlight for studying the later universe. When this ancient light passes through galaxy clusters, it gets slightly distorted by hot gas through the Sunyaev-Zeldovich effect. These distortions allow astronomers to detect galaxy clusters and map their properties across cosmic time. Some regions of space show shadows in the cosmic microwave background where intervening matter has absorbed or scattered the ancient photons. These shadows trace the large-scale structure of the universe and provide independent confirmation of dark matter distributions. But compared to what comes next, this ancient light only illuminates the observable portion of a universe that extends far beyond our cosmic horizon. The observable universe represents just a tiny bubble within a cosmos that may extend infinitely in all directions. We can only see light that has had time to reach us since the Big Bang, creating a spherical boundary 46 billion light-years away. Beyond this cosmic horizon lies more universe, potentially infinite in extent, that remains forever hidden from our view. Light from the edge of our observable universe has been traveling toward us for 13.8 billion years. But cosmic expansion has carried those distant regions much farther away during the light travel time. The galaxies that emitted the cosmic microwave background radiation we detect today now lie 46 billion light-years from us, well beyond what we can ever hope to reach. But here's what makes the universe's true size so mind-boggling. Cosmic inflation theory suggests that the entire universe is much larger than the part we can observe. During the first fraction of a second after the Big Bang, space expanded exponentially, stretching a region smaller than a proton to a size larger than a grapefruit in less than a trillionth of a trillionth of a trillionth of a second. Observable portion. This means that if the observable universe were shrunk to the size of a light bulb, the actual universe would still be larger than Earth. More extreme inflation models propose that the universe could be infinitely large, containing infinite matter and energy. An infinite universe would contain infinite copies of everything, including exact duplicates of you, Earth, and our entire observable region. The laws of probability guarantee that every possible arrangement of matter would occur infinitely many times across infinite space. This leads to the bizarre conclusion that there are infinite versions of you reading these exact words right now. Even if the universe is finite, it's almost certainly much larger than we can observe. Current measurements suggest that if the universe has positive curvature and finite volume, it must be at least 400 times larger than our observable bubble. A universe with negative curvature or flat geometry could be infinite in size. The cosmic horizon also grows with time as light from more distant regions reaches us. Every year, our observable universe increases in radius by 1 light-year. But cosmic acceleration means that galaxies beyond a certain distance are moving away faster than light, creating regions we will never observe, no matter how long we wait. Future observations might provide indirect evidence for the universe's true size. Gravitational waves could potentially carry information from beyond our cosmic horizon. Cosmic inflation might have left signatures in the cosmic microwave background that constrain the universe's total volume. But compared to what comes next, even an infinite universe might be just one bubble in something far grander. Beyond our cosmic horizon stretches more space, more galaxies, and more cosmic structure extending potentially forever in all directions. This unreachable realm contains the same physics, the same types of stars and planets, and possibly the same patterns we observe in our local cosmic neighborhood. But we will never know for certain what lies in these forever hidden regions. If the universe is infinite, then every possible arrangement of matter exists somewhere beyond our view. There would be regions where stars never formed, leaving space permanently dark. Other regions might contain galaxy clusters far denser than anything in our observable bubble. Some areas might have evolved completely differently if the local values of physical constants vary across cosmic distances. But here's what makes the unobservable universe so tantalizing. It might contain the answers to our deepest questions about cosmic structure. The largest structures we observe in our cosmic neighborhood, great walls and superclusters, might be just small portions of even larger patterns that extend beyond our horizon. The true cosmic web might be far grander than anything we can imagine. Eternal inflation theory proposes that our observable universe is just one bubble in an infinite multiverse. In this scenario, cosmic inflation never completely stopped, but continues creating new regions of space at exponential rates. Our Big Bang represents just one local event where inflation ended, allowing matter and energy to condense into stars and galaxies. Each inflation bubble would have its own physics determined by how the fundamental fields settled into their current values. Some bubbles might have stronger gravity, making stars form more easily but burn out faster. Others might have weaker electromagnetic forces, preventing atoms from forming at all. Most bubbles might be completely unsuitable for any form of structure or life. The boundaries between different inflation bubbles would represent the most dramatic transitions in the multiverse, where two bubbles with different physics meet. The interface might trigger exotic phenomena unlike anything in our local physics. These bubble collisions might leave signatures in our cosmic microwave background, though detecting such evidence remains highly speculative. Some theories suggest the unobservable universe might have different dimensions of space and time. String theory allows for up to 11 dimensions, though only 3 spatial dimensions appear large in our local region. Beyond our horizon, space might unfold into higher dimensions, creating geometries impossible to visualize from our limited perspective. The unobservable universe also raises profound questions about the nature of scientific knowledge. If we can never observe or interact with these regions, do they represent legitimate subjects for scientific inquiry? The answer may determine whether cosmology remains a physical science or becomes a branch of philosophy. But compared to what comes next, even infinite space might represent just one aspect of cosmic reality's true scope. Just after the Big Bang, something extraordinary happened. In less than a trillionth of a second, about 10 to the power of minus 35 seconds, a region of space smaller than a proton balloon to the size of a grapefruit. This sudden burst, called cosmic inflation, stretched the universe by at least 10 to the power of 26 times. Tiny quantum ripples were magnified into the seeds of galaxies, while space itself expanded far beyond anything we could ever hope to explore. One of the biggest puzzles in cosmology is the horizon problem: why the universe looks so smooth and uniform everywhere we look. Inflation solved this by taking a minuscule, connected patch of space and stretching it to cosmic proportions. In fact, every part of the universe we see today was once squeezed together into something smaller than a subatomic particle. That's why the cosmic microwave background, the afterglow of the Big Bang, has nearly the same temperature in every direction, even though distant regions could never have directly spoken to each other. But here's the truly astonishing part. What we call the observable universe, everything we can see with our telescopes, might be just the tiniest fragment of what inflation produced. The region that inflated was at least 10 to the power of 23 times larger than what we can observe. Imagine blowing up a balloon until it's the size of Earth, then realizing that our entire observable cosmos fits into an area smaller than a single atom on its surface. Most of the universe lies forever beyond our horizon, containing the same physics and probably the same kinds of galaxies, stars, and planets. There may even be countless versions of the Milky Way, countless Earth-like worlds, and countless beings like us scattered across this vast expanse. Now take this idea further with what scientists call eternal inflation. If inflation never completely ends, then new regions of space keep forming endlessly, each expanding at exponential speeds. Our Big Bang would just be one small pocket where inflation stopped, allowing energy to turn into matter and light. Elsewhere, inflation could still be running, creating bubble after bubble, each potentially with different physical laws. In this picture, the total universe becomes truly infinite, filled with infinite galaxies, infinite matter, and infinite versions of everything that can possibly exist. Every quantum possibility would happen somewhere, meaning there could be endless variations of cosmic history playing out across an infinite multiverse. Observations strongly hint that inflation is real. The flatness and uniformity of the universe, along with the specific patterns in the cosmic microwave background, fit perfectly with inflation's predictions. In the future, scientists may even detect ancient gravitational waves, ripples from those earliest moments, that would serve as direct evidence. So, how big is the universe? If inflation is correct, the answer is breathtaking. It's either so vast that we'll never measure its full extent, or it's literally infinite. In that case, everything we see, every star, galaxy, and structure in the sky, is less than a drop compared to the true cosmic ocean. The universe began smaller than the dot at the end of this sentence, yet it grew into a reality so immense that we can hardly begin to grasp its size.